Hey guys, what's going on? So today we're going to continue working on Yukawa interactions. We're going to be doing the first order and the second order approximation to these Feynman diagrams, and then we're going to move on to other things. So without further ado, make sure to hit that like and subscribe button, and let's get into the content. So we're talking about first order approximations now to the Yukawa interactions. Okay, so this is actually kind of interesting because what we're going to find is that the first order approximation actually doesn't contribute at all to these interactions, and here's why. So here's our first order term, right? So this came from, if we go back here, this is our first term in the interaction. It came from, again, the Dyson series. So if we go back, I just copy pasted it here, and then we take the let's see here. We're taking an I. So here we have the I. So here is our time evolution operator, or not time evolution. This is our time ordered product with our normal ordered product, and then. So nothing really that exciting is going on in this derivation, but what we're going to see here is that, okay, we take this G out, right? So this is a coupling constant. This is just constant. What's interesting about this is that we now have this. So nothing really changed, but when we look at this, there's three terms here, right? If we go back for a second to here, we have four terms here, right? We have a particle in the initial state, another particle in the initial state, then a particle in the final state, another particle in the final state. We were able to contract one with another one, right? So we contracted this one with this one, and we were still left with two left over to contract. So everything's been contracted here. Everything can get contracted here, and everything can get contracted here. But if we have three terms, we can contract this guy and maybe this guy, right? We can contract him, say, with this guy, and we can say contract this guy with this guy, and then we could say contract this guy with this one, but we're left with a question mark on this guy, right? So this is interesting because we have something that's always never going to be contracted in this first order case. And so what does this leave us? Well, if we come down here, because there's three terms in the interaction Hamiltonian, one field will always remain uncontracted, right? So something is going to always remain uncontracted. What does that mean? Well, if we recall, here's our time order, here's our normal order, here's our contraction. Any field that's not contracted, right, is going to be left within a normal order, or outside of a normal order, right? So effectively, this term is going to go to zero, right? This doesn't really make sense, right? Effectively, what we're saying here is that if a field is left uncontracted, then it's going to make everything go to zero, right? Because it's the case because here we have two contracted. If we had another guy here, right, say another field, well, that means we're going to have another field out here. We're going to have another field out here and another field out here. And so, but if we have another field right here, then this guy is going to make everything go to zero, because everything normal ordered is going to go to zero. And so, again, this is it's kind of a weird thing to get our heads wrapped around. But the idea here is that if we have three terms, here, one guy is always going to get left uncontracted. And if one guy is always left uncontracted, then the whole thing's just going to go to zero. Right? Because when you time order something and there's no contraction with whatever that's being time ordered, then all you're left with is a normal order. And we've made this so that normal orders always go to zero. So effectively, the first order approximation to a Yukawa interaction has no contribution whatsoever. So we move on to the second order approximation, which is in this next slide. So the second order approximation is where things get a little bit complicated. So let's do this. So we have our second order approximation, and this is what it looked like, right? We had this huge, long thing. And the reason this is long, is here, if we go back for a second, here's our second order term, right? We have the interaction Hamiltonian twice. This came from the Dyson series again. And so our interaction Hamiltonian, what we put into our interaction Hamiltonian is our Yukawa interaction, this guy. So we come back to our... So here, this guy right here is our Hamiltonian. And this guy right here is our Hamiltonian, right? The only difference between these two is that we are integrating at one space-time point, x1, right? So this is our Hamiltonian at x1, and this is our interaction Hamiltonian over here at x2. So this is our second space-time point. So this is the particles coming in at one point, that's x1, and then the next vertex is at x2. Right, so I can draw that. If I draw that, this is x1, and this is x2. These are space-time points, remember. Okay, and we can see, so we can see here, again, here's our initial state. We go through a space-time point. One space-time point, we go through another space-time point, and we end up at our initial, or our final configuration with some constants out here. So we can actually, so we'll take the time, the time order operator inside the integral, and we take our constants. So we have two interaction constants. We take those two outside. Right? This times this is squared, which is out here, and then we have this 2 factorial. Again, this comes from the Dyson series. So that is all this, right? So again, what we want to do now is we have the time order, we have the normal order. The difference between the time order and the normal order is the contractions. Now this is where things get a little bit hard, or not, I wouldn't say hard, but a little bit meticulous. The reason for this is because we have 2 contraction terms, and these things are pretty long. Or you could see how long these contractions are. Like the sheer length of each contraction is sort of daunting. But let's take this. We're going to do one contraction, and then I'm going to say by analogy you can work out the other one, because that'll just make this video, I think, unnecessarily long. Anyways, so all these guys are at x2, or space-time point x2. All these guys here are at space-time point x1. So here, this guy here, we're contracting with an initial state. And this guy here, we're contracting with an initial state. And these two are the only two that are actually permissible, because the final state is, remember, the complex conjugate. It's the ket, or it's the bra state, whereas the ket state is not the complex conjugate. So we need the fields that are not complex conjugated to contract with these guys, and the fields that are complex conjugated to be contracted with these guys. Because if you have something that is complex conjugated multiplied or contracted with something that is not complex conjugated, then that's not gonna exactly work out very well, because if we can do the mathematics, and it'll show that'll end up going to 0. And so this is really one of the only contractions we care about. The other one we care about is this guy right here, right? So this guy is going to go here, and this guy is going to contract to this guy. And then this guy here contracted, and this guy here contracted with here. These two scalar fields, right? So these two scalar fields are contracted with each other. They cannot contract with these guys because, again, we're defining these particles to be complex in nature, right? So these are the complex scalars. So we contract the real scalars with each other. Same thing goes for here. We're complexing the real scalars with each other. Okay, so we go through all this with that video on important contractions. So you can go back to that video if you wrote all the important contractions down, and we have this guy right here, and I think we need a 0 right there. So where does this leave us now? This takes us to this guy right here. So we combine all the exponentials together, right? All the exponentials together, that's right here, and then we have our propagator, our Feynman propagator, going from space-time point x1 to space-time point x2. And then what we have going on is now putting everything back into this expression here for our A2. Right, so I kind of just worked out this argument inside the integral first, and then I came to this point, and now I'm putting it back inside the integral because we still need to deal with the integral. So here's what it looks like right here. And then let's see what we're doing here. So we have not much. We're just plugging in the Feynman propagator now. We went over this before. So again, nothing much going on. We then take the Q, distribute it across these two guys, and then distribute it within these two guys. Right, so that we get these two exponentials. Okay. And then this integral, right, so this 2 pi to the 4th gets moved over. It's just a constant. And then here's the denominator to the propagator. So we're just moving things around, basically, here. This I right here gets pulled out. It's a constant. All right. And then we get, so from here, we get to this guy. Okay, so again, here, this guy, and then this guy here, and this guy here. Again, this is Fourier analysis, where we have a wave, and we're locating the frequency of that wave with a spike. So that's these two guys, and that helps us get rid of these two integration factors. Also, this from here to here. I will reiterate this point. From here to here, this is Fourier analysis. Okay, then we do this little trick here. To get from here to here, we want to recall something, that the integral of some function, this is just a dummy variable, x prime, it's not a derivative, excuse me, this is some dummy variable. The integral of this, when we have a delta function at this dummy variable, will just give us the function, right? So this is something from calculus. And so zooming back out here, our function, right? So our delta function is going to be right here, okay? And our f of x is this guy, right? So this is our f of x, and we're just putting in k4 minus k2 for q, because remember q is this variable that conserves our forward momentum. We'll plug that in for q here also. Right, so this guy here, I'll just write that down explicitly. This is q, and this is q. And we'll see here, actually, I'll erase that actually because I have it already written down. So we come down here to this point. So everything out here is pretty much the same as right here. We change this guy to a t squared, and everything stays the same. So essentially our answer has come down to this point down here. And t we're calling a Mandelstrom variable, right? So this is, again, this is really just a conservation momentum variable. This is something that, a little bookkeeping device that is, this is the thing that we were aiming to put a threshold value on when we were doing renormalization coupling, and we're going to come back to that later also. But anyways, here's our other contraction, and so all of this that I've done, all the way down to this point, we can do the same exact thing basically for this guy right here. That's why I have all these arrows. And we skip all that and we come down to the answer where u is also a Mandelstrom variable that equals these two guys down right here. That's right. So this is what we have, right? So we have this guy and this guy. So that takes us to this last slide here. So therefore, our second order approximation for our Yukawa interaction looks like this. Right? So this is essentially our answer. I'll box this guy. That's essentially our answer for what we get for our second order approximation. Now you might think, okay, this is kind of long, it's not really satisfying to look at. Not a very, maybe a little bit of a beautiful equation, but still, what can we make of this? Well, t again this is our Mandelstrom variable, u is a Mandelstrom variable. Each term, this is kind of interesting, each term, and these guys should be squared actually. Those guys should be squared. We could think of this as, okay, K4 and K2. So here's K4 and K2. And here's K3 and K1, right? So this is, again, a conservation of momentum principle. We're saying that you could essentially say that the momentum change between 4 and 2 is equal to the momentum change between 3 and 1. Whereas the other term accounts for the potential outcome in which there's the difference between 4 and 1 are the same as the difference between 3 and 2. Right, so we can see here that our second order approximation to our Yukawa interactions, our second order approximation to our Yukawa interaction accounts for two scenarios. One scenario being the situation in which the difference between the momentum 4 and 2 is the same as 3 and 4, and the other situation in which the situation between 4 and 1 is the same as 3 and 2. So there's two possible outcomes, or the two possible situations that the second order approximation brings to us. And this takes us to our last and final idea here, the idea of spinors. And we're going to get into this when we talk about gauge interactions next. For spinors, the Feynman rules are pretty much the same, right? So what we've been doing is we've been saying that for incoming particles, we have this term right here. For outgoing particles, we have this term right here. Well, for spinors, we just add our spinor components, right? So we're going to have spin up particles, right? We're going to have spin down particles. We're going to have spinners, and we're going to have anti-spinners. So there's 4 things that we're going to want to bookkeep for later on when we do gauge interactions. Because in gauge interactions, we're going to look at Bahaba scattering, and it's going to be very useful to bookkeep not just what the form momentum is going in and coming out of our black box, but also what the spin is in our initial and final states going before and after our black box as well, right? So there's 2. So I'll actually write this down because we want to keep this in mind. This is so there's 2 things we want to keep track of. One is momentum, and the other is spin. Same thing for our initial states, right? So initial states, final states, and we want to keep track of our momentum and our spin. And so the way we keep track of momentum, again, that's kind of done for us already. So we don't really need to do that. Keeping track of the momentum, it comes in the form of these Mandelstam variables right here. Keeping track of the spin is going to require something else, and that's going to introduce or bring into the picture our Dirac gamma matrices. And so for our Yukawa interactions, if we're dealing with spinors instead of complex scalars, we have our answer looking like this, right? So we have our spin, these are our spinors right here, right? So outgoing spinor, incoming spinor, outgoing spinor, incoming spinor, and then same thing for these guys here. And we're going to get into this later also. We're going to learn how to bookkeep what the spin is when we look at Feynman diagrams. But anyway, this is kind of a long video, so I'll call it here. Now, so what we've done is we've gone over Feynman diagrams, we've gone over Wick's theorem, we've gone over a lot of stuff, right? We've gone over Yukawa interactions. The next thing we're going to be going over is gauge interactions. And we're going to also be covering the renormalization group, which is very interesting. And so, with that being said, I hope you guys like this kind of content, and I'll see you guys in the next one.